is there a Gauss's law-like shortcut that we could use in magnetostatics? It'd be great. Whenever you have a symmetric system, it would save a lot of time. In Gauss's law, you'll recall that we try to construct a three-dimensional surface, and then we find the flux going through it. Now, in electrostatics, the electric flux is equal to the charge enclosed by the surface. But what is the equivalent in magnetostatics of a charge enclosed? What is the magnetic equivalent of enclosed charge? Well, there's no magnetic analogue of charge. There's no such thing as a magnetic north particle, for example. Magnetic particles also always exist in pairs, as dipoles. We say they are north-south. What that means is that the enclosed magnetic charge has to be zero. And hence, the flux has to be zero. For all the flux that you have coming out, it must also circulate somehow back in through the surface. So let's think of a more useful expression. And for us, it's Ampere's law. Our current, which is a flow of charges moving at constant velocity, is the source of the magnetic field. Here's our current, travelling along a wire in this case. Ampere's law says that the current that passes through a surface, let's draw a surface here, the current that passes through this surface is proportional to the amount of magnetic field not going through but circulating around the boundary of this surface. Okay, so we're going to draw, and this is our so-called Amperian path, just as we drew a Gaussian surface in the electrostatic problems. The right thumb indicates the direction of positive current, and the fingers of your right hand indicate the direction that we are going to go around this path. This video will help you remember what it means to do a line integral along a curve. In this case, the curve is open, it doesn't close on itself. The integral starts from position A. At each position, we take the little red arrow, which indicates the direction of the curve at that point. Then we take the dot product of that with the blue arrow at that point, which is the strength and direction of the vector field, also at that point. And we complete this procedure all the way along the curve from A to B. The integral is the area under the curve, which you see down the bottom of the animation. So let's draw Ampere's law expression here. we're going to integrate, you can see from this circle, around a closed path of our magnetic field parallel to the element of the Amperian path as we go around. And this is going to be the current, the enclosed current, that is the current that is going through this surface that we have created. So at this point here, we would say that is our dl, and you can see it has a little direction like that. And our magnetic field, well, what we need to know whatever it is at that point as well. Say, for example, it is also in that direction. It's going to be parallel to dl, isn't it, there? And we go around this path, taking the dot product of dl and whatever the magnetic field is at that point. We add them all up, and that is equal to the current that's going through that surface. As you might expect, currents which have some special symmetry, for example, if you can draw a path where the magnitude of the B magnetic flux density is constant all the way around that path, this law becomes a really efficient and lovely way of finding the magnetic field.